Hello, it's Michelle here, and today we are going to look at the hand computations behind a one-way ANOVA. And here, when we refer to one-way, we are meaning a one-way between subjects ANOVA, SS short for subjects, not sum of squares. And for our example, we're going to assume that we have data from 3 independent groups, and we want to discover with hand calculations if there is a difference between at least 2 of these groups. So from before, when we computed t-tests together, we had group 1 and group 2, and we determined that the mean of group 1 was 1.8, but the standard deviation was 0.837, and for group 2, the mean was 3.2, and the standard deviation was the same as group 1, 0.837. And for group 3, if you feel that you need a warm-up or maybe a bit of a refresher on how to just compute a mean and a standard deviation, or you just feel like that would be a fun, valuable use of your time, why don't you go ahead right now and compute those to your satisfaction while I do it alongside you. So the mean of group 3 is 7, even, and our standard deviation of group 3 is 4.743. We keep 3 decimal places for calculation purposes. So one thing to notice now that we have our descriptive statistics here is that standard deviation of group 1 and group 2 are both quite a bit smaller relatively to the standard deviation of group 3. And so one question we might ask is, are they at least 2 times apart? And the reason why we're asking if they're at least 2 times apart is because we have a rule that if the variances of the groups are at least 4 times apart, then we may have an issue with the homogeneity of variance assumption. And in this case, we can see that it certainly appears that way. For example, we could divide S3, the bigger standard deviation, by S1, and we would end up getting 4.743 divided by 0.837, which gives us around 5.7. So S3 is 5.7-ish more times than S1. So, I mean, yes, indeed. Now, this was done on purpose. This toy data that we have and are going to be working with can give us some insights into certain things, one of which is a Levene's test that is used in SPSS that we examine in order to determine whether or not we do have an issue with homogeneity of variance. Now, what that would imply is that the equal variances assumption cannot be assumed. And as a matter of fact, I do believe from my hand computations I did a while ago that there is a barely significant Levene's test, meaning that there is a violation of that assumption. But typically, in case you're wondering, Levene's violations tend to be rare. So it takes a lot of difference in variances, or standard deviations if you like, to cause a Levene's test to be significant. So now let us start to compute our F ratio by hand. F for this one-way between subjects ANOVA is the mean squared group divided by the mean squared error. You could also label it MSE, mean squared error, which is in fact how we report our result in this APA style with an italicized MSE symbol. But I take the technique that I use a subscript to describe what my mean squares are, so it's a bit of a habit. And I think it's helpful too sometimes to write things out when we're trying to understand or learn things. Acronyms, for example, might be not our friends when we're being introduced to new stuff. So that said, that's my MS error. So in order to compute this F ratio, we need the following. We need the sum of squares group. We need to know how much variance in the scores can be accounted for by the fact that the groups themselves are different, that our manipulation is causing variation in the scores. That is equal to n times the sum of, for this example, we have 3 groups, so j equals 1 to 3, of xj bar, the mean of each of the groups, each in turn minus the grand mean, and resquare that. We also need the sum of squares error. That's the other quantity that we need. Now, there's a couple of ways that we can do SS error. The first one is we could obtain the total sum of squares for this data and subtract off the sum of squares group after we compute that. So that's one common way of doing that. Or there's a direct formula for that as well that might help us conceptually understand what SS error means. So, or we could look at each group individually, starting with the first one. So each of those 5 observations, and looking at those deviations from their own group mean, so how different stuff is within its own group, and then do the same for group 2. I'm going to run a room, scared, and then do the same for group 3. So we look at all the individual scores and look at how they deviate from the group mean of 7. Yeah, I did it. So this would be the formula that we would use to compute SS error by hand. And indeed, we are going to see both of those computed today. Well, before we can compute any of the sums of squares in order to get us to our F ratio, we are going to need our grand mean. So when I write this symbol, which is x bar dot dot, that means grand mean. And the reason that I am clarifying this is because generally we have been using this dot notation for big fat means, like our grand mean of everything, for example. But sometimes you may see, depending on what resource you use, x bar GM for grand mean, which was just recently introduced in some of the textbooks. So I think just my concern is that the more traditional notation might be confused, but these are the same thing. And while we do our best to stick to a certain notation, we can definitely accidentally use a different one and cause confusion. So just keep in touch with us, clarifying with us on which notation might be easier for you to use and to follow the course material, or which might be favorable. So we need our grand mean, which I just refer to as x bar dot dot. And in order to find that, we are going to have to sum all the stuff that we have, so stuff meaning observations, and we have to subtract. Oh, we don't subtract anything. It's a mean. I'm so used to writing sums of squares. So we'll just divide then by the number of observations, which is 15. Would it be the same, exact same grand mean, if we had taken an easier approach and looked at the individual group means and computed the average of the individual group means? So that's 1.8 plus 3.2 plus 7. Already been computed from these observations, so there's only 3 means And then when we compute the mean of means, what happens? So while I leave you to conclude, indeed, we should get exactly 4. And the thing about this method, sometimes we caution against it because it will only work to take the mean of already means if the number of observations that contributed to each of these means are equal. So since there's 5 here, 5 here, and 5 here, we will always be able to get the same number, whether we take a mean of means or whether we take a mean of observations from scratch. However, a lot of caution needs to be taken if there is at least one cell or a group with different numbers of observations in it. So it's only if n's are equal. So now you have a shortcut sometimes. So as was up a little earlier, our SS group formula looks like n times the sum of group means deviating from the grand mean squared. And this n, this is the number of observations per group. And it is, in our case, 5. So we can start to sub in some numbers here. I'll go in an unspeeded fashion for this because we're trying to learn this new computation. So SS group then is equal to 5. What I like to do is like this is like a bunch of sums of, like it's a sum of squares, bunch of squares. And so I like to kind of open up a square bracket. So 1.8, my first mean minus the grand mean squared, plus my second group mean, 3.2. Just kidding, don't close the bracket yet. Minus the grand mean, 4, plus 7, the third group mean, minus the grand mean of 4. And then we work our way through, so that's equal to 5 times this is 4.84, this is 0.64, this is 9. And so we have 5 times 14.48, and that is equal to 72.4. It's a unitless quantity. 72.4 represents the total variation due to the fact that we have 3 different groups. What remains now is for us to compute sum of squares error. So for SS error, there are 2 ways. Way number 1 is to compute SS total and subtract our SS group, which we've just found to be 72.4. That number should always be positive, and it'll give us the sum of squares error. In order to do this, you would need to compute SS total. So there then was kind of a long-winded computation of SS total with a little bit of arithmetic simplification so that I didn't make a mistake, or at least had less likelihood of making one. It's a little tedious, I'm sure, but it's not so bad when you have 15 points altogether. Computing SS total once in your life for a mini tiny data set like this one wouldn't hurt at all. It would be just one nice experience to get you closer to conceptual understanding of how ANOVA works. Now that we have that SS total is 168, we can subtract SS group, or 72.4, and arrive at SS error, which is 95.6. Now, there is another way. So way number 2. Okay, my marker's running out, and it's all thunderstormy outside, and I'm just like, the marker's getting fainter, and then the weather's getting darker. This is going to be a contrast issue. Okay, so let's switch colors and hope that that works. So for way number 2 is kind of the direct formula for SS error, which assesses how much these observations are moving around within group 1 and these observations within group 2 and so on. So for way number 2, we are going to compute the sum of squares associated with deviations from this mean. So that would be written as xi minus x1 bar squared. So that's for mean ones. And then same kind of idea from 1 to 5. Individual observations denoted by x sub I, but then we're just going to subtract x2, mean 2 rather. And then we're going to add to that some more error. So I equals 1 to 5 of xi minus x bar, but 3, the third. Ah, I cubed it. Oh my gosh, it's just not okay. All right, so that is way number 2. If you'd like to give that a try, again, just to see how it is that these different data fit together to create an error, please, by all means, go right ahead. There we have it. Both of our computation methods have given us our sums of squares error, 95.6. So now we have to calculate the mean squareds. So M as group, which will be on the numerator of our F, is equal to the sum of squares group divided by kind of a weighting factor that is sort of like a mean. That's why it's called a mean squared from the sum of squareds. And that's the degrees of freedom, or DF group. So sum of squareds group we have on the left is 72.4. While the degrees of freedom for group is the number of groups minus 1. It's a between subject design with 3 groups. Therefore, we'll be dividing 72.4 by 3 minus 1, or 2. And when we do that, we end up getting 36.2. MS error. Did you see that incredibly smooth transition to this new section of the video, by the way? Is equal to sum of squares error divided by degrees of freedom error. So degrees of freedom error also have their own formula. And so what we would do is the SS error would be 95.6. And then we would be dividing by these degrees of freedom. And the formula that if you wanted to use a formula, would be K times n minus 1. And so what this is this is the number of groups, and then this n over here is the number of observations per group. So I've just kind of explained what the letters in a formula means, but I haven't really explained what the what the idea is here. So the idea is you look in each of these groups and you take the degrees of freedom of each of them individually. So the degrees of freedom, as if you're taking the degrees of freedom total. So you have 5 observations in group 1. So that means kind of 4 degrees of freedom just for that group. And then same here, we have 5, so 4 degrees of freedom for group 2 and 4 degrees of freedom for group 3. So then what you do is you just add those up, 4 plus 4 plus 4, or 3 times 4. Okay, my dog has decided to extremely loudly drink water. This is excellent timing. I'm going to ignore it. So in this case, k is 3, n is 5, so it's 95.6 divided by 3 times 5 minus 1, as we discussed, or 3 times 4, so 95.6, divided by 12. And so now that's our degrees of freedom error, 12. And when we finish this computation, we end up getting, can you see that? Yep, okay, cool. You're getting 7.967, 3 decimal places. Okay then, we are now at the end. I don't think any animals in my house are thirsty. You just gotta love the work from home, right guys? All right, so let us complete our computation. Our F ratio is MS group. What influence are the 3 groups having on our data? And MS error. What influence are the within group observations having on our data? And so we get 36.2 divided by 7.967, and that gives us 4.544, rounded to 3 decimal places for good measure. However, when we are going to report our result, we are going to have an F, degrees of freedom group, comma, degrees of freedom error, and that is going to be set equal to our F ratio, F value, F statistic, whatever you want to call it. And that is going to be rounded to 2 decimal places. Now, you may be wondering what significance this F has. If we looked it up in the table, I could tell you that the table gives, here we go, F crit equals 3.89, rounded to 2 decimal places. You can keep 3 decimal places. I lost the last one. It just got lost. So basically, because our critical F value is exceeded by our observed F value, we know that we have a significant F test. And what does that mean? At least 2 of these means differ.